All right, so we're going to continue along with this 2014 released AP exam, AB. We're going to do numbers 17 through 22 of the no calculator section of the multiple choice. On number 17, we're finding the derivative, it says, of this exponential function with base e. And notice we've got these generic numbers a. So just think about them as being like a number like 4, 5, or 6, and how would you do this? So the derivative of e to the u is just e to the u. So the derivative of this would be a e to the negative ax, just completely unchanged, but you always multiply by the derivative of the inside function. So here's the inside function. So if we multiply by the derivative of that would be negative a, right? If that were negative 5x, the derivative would be negative 5. So we end up getting negative a squared e to the negative ax. So that's the answer right there. Really easy one. You should be able to do that one pretty quickly if you just recognize a is just a number. Okay, here we go. Number 18. A student attempted to solve this differential equation with the initial condition 2 and 0, so 0, 2, for example. At which step did they mess up? So remember, when you solve a differential equation, you separate the x and y. So the y goes over with the dy by dividing both sides by y. That's why it landed on the bottom. And on the right side, I end up with x dx. And then you're going to take the antiderivative. And that's what they've done there. And that all looks good. Now, in step 2, what they've done is they've done the antiderivative. So this would be ln absolute y equals 1/2 x squared plus c. So that all looks good. They did the power rule in reverse, and of course the antiderivative of 1 over y is ln y with the absolute value. Now what did they do? They got rid of the natural log by basically putting a base e on both sides, but they didn't quite do it correctly. This plus c shouldn't just be slapped at the end because of the, look what I did here. It's actually should be up in the exponent, or if remember when you're adding exponents like that, it's the same thing as multiplying. So you could think of that as e to the c being up there. So right there was the mistake, because if you plug y equals 2, by the way, this is equal to, so then if you plug y equals 2 in there, and x equals 0, you get e to the 0, e to the c. Now this is just 1, so e to the c is 2, so that means c equals the natural log of 2, not what they have there. So it really went wrong on step 3, and B is the correct answer. All right, moving on to the next one here. For what values of x does the graph have a point of inflection? So ask yourself, okay, so what do we look for here? We look for when f double prime changes sign. So if it changes from negative positive or positive negative, that's how we know we have a point of inflection, when the concavity changes, and the second derivative is where concavity comes from. So we got to find the second derivative, so let's do that. The first derivative would be 15x to the fourth plus 40x to the third. The second derivative is 60x to the third plus 120x squared. You know, this is the no calculator section, so you kind of hope that the numbers are going to work out nicely. You now factor it. 60x squared gets factored out. That leaves x plus 2. So the critical points that we need to look at, where we think just maybe there's a point of inflection, would come from x equals 0 and x equals negative 2. That's the 0 on there. Now I like to do a sign chart like this, where I have my critical values, and then I have my intervals that I'm going to look at. All right, and we're going to look at f double prime. So you can come back right here. Imagine plugging negative bazillion in here. This term is going to win, and it's going to be negative. So this is going to be negative. If you plug positive infinity, we're going to end up with positive. So we really need to know what's going on in this interval right here. I like to plug -1 in. That's the easiest thing. So let's come up here. 60 times -1 to the third power, that's just -60. And then, of course, anything squared is positive. So plus 120 times -1 squared is plus 120. That is positive 60. All we care about is the sign. So this is concave up there. The original function is concave up. So we have a point of inflection at -2 only. -2 only. That's where the sign changed. Didn't really care about analyzing that first derivative here. Number 20. Number 20. Which of these is the right answer? This is kind of a crazy one. You look at it for a little while, limit, you can't plug 2 in here because you get an over 0 problem. Now you can plug, you can't plug 0 in the top either, right? Can't plug 0 in the top either because you end up getting ln5 minus ln5. That's just 0. So how do you deal with a situation when you have 0 over 0? That L'Hopital's rule. L'Hopital's rule says that you can take the derivative of the top, the derivative of the bottom, and evaluate on the same limit. So here we go. What's the derivative of natural log x plus 3? By the way, we're not doing the quotient rule. We're taking the derivative of the top and the bottom separately in L'Hopital's rule. Okay, so no quotient rule here. I don't know what made me think about that, but we do not do the quotient rule. So this would be 1 over u, right? So 1 over x plus 3, there is no chain to tack on, minus the derivative of a constant is just 0. That's nice. And then the bottom, the derivative of x minus 2 is 1. Now can you plug in 2 safely without any divide by 0 problems? Hey, you bet. We plug it in there, we get 1/5 minus 0 all over 1 is just 1/5. That's the answer. That wasn't so bad. It looked kind of crazy at first. All right, moving on. Number 21. We have functions w, x, and y, and they're all differentiable with respect to time. Uh-oh, it sounds like a rate of change problem. Okay, our related rates by the equation w equals, okay, so we've got this here, w equals x squared y. If x is decreasing at a rate of, okay, so that's why I write dx dt. I always use the Leibniz notation. Decreasing means it's going down by 1. So I convert it to Leibniz notation as I'm reading it. Okay, and then it says, and y is increasing, so that means dy dt is going up by 4. At what rate of change? So they're asking dw dt is what? That's what we're going to solve for here in a moment. When x equals 6 and y equals 20. All right, so I really encourage you to try to jot things down like I did off to the right there on the screen. And then let's take the derivative implicitly like you learned how to do in the related rates. So we start with that. So if we take the derivative, we would get dw dt, whatever the derivative is with respect to t. Now on the right, what do we have there? Let me hear you. The product rule. That is a product. Careful about this. So we take the first times the derivative of the second, which is just dy dt, plus the derivative of the first is 2x, but, x is a function, remember, so you have to put a dx dt there. You probably know that. I'm just making sure you remember. And then times the second. So that is just the product rule. Product rule. And we have everything. We have x equals 6, so this would be 6 squared. We have y equals 20. This would be a 20 over here. 2 times 6. And then off to the right here, let me bring it back to the screen there for you, we have that dx dt is -1 and dy dt is -4. We wrote that down a moment ago. So we put the 4 here. I think I said -4, but it's +4. It's because it's increasing. So dy dt is +4, dx dt is -1. All right, so this is 36 times 4, which is 144. This is going to be minus because 2 times 6 times negative 1 is minus, I'm sorry, this is 36 times 4. Let me check this again. Yeah, 144 minus, we have 2 times 6 times 20 is minus 240. I don't know what I was thinking there. I was thinking 120, but there we go. 144 minus 240 is negative 96. And that's the answer right there. All right, so the no calculator section kind of tripped me up there for a second where I had to make sure I didn't make some silly mistakes. So you do the same. Just be careful with your arithmetic. You don't want to do all the calculus right and then mess up there. One more question on this video. This is a little bit of a longer one. Let f be the function defined. We've got a cubic. When is it decreasing? Okay, so what are we looking for? So the function f will be decreasing when the first derivative is negative. And also, the original function is concave up. So that's, so it's going to be concave up when the second derivative is positive. So we're going to have to do both derivatives. We're going to have to do sign charts on both of them and figure out the overlap. That's the strategy. You kind of have to have a game plan going into these, right? So let's get the first derivative. Let's just deal with the first derivative first. That would be 6x squared minus 6x minus 12. I go ahead and factor because I see what's going to happen here. I can factor this into x minus 2, x plus 1. So I see x equals 2. These are my critical points. X equals 2 and x equals negative 1 are my critical points. So we come over here, and some of you like to use a number line. Let's do that. Here's 0. Here's 2. Okay? So from negative infinity, over here, negative infinity, all the way up to negative 1, let's plug in and see. Negative infinity squared is positive infinity. So you know what? That's going to beat everything out, and we're going to end up being positive. Let me use a different color so it stands out. Positive over here, and positive up here, of course. You know, when you plug positive infinity, all we have to do is check in the middle, and if you plug 0 in, you get negative 12. Aha, negative 12. So we're looking for when is the first derivative negative. So far we have negative 1 all the way up to 2. We still have to look at the second derivative to see where the overlap is on that number line. So let's come over to the side here. I'll do this in a different color. We'll use red over here. I'm going to do the second derivative so that I can do a sign chart on that. That's 12x minus 6. If you factor that, that's 6 times the quantity 2x minus 1. If you set that equal to 0, you see x equals 1/2 is the critical point. So on our number line, negative infinity all the way to infinity, here's 0, here's 1/2. So let's plug negative bazillion into this. Do you get negative or positive? You plug negative 1 million. Negative. Okay, so that means concave down. Concave down. Concave down right there. And what about positive infinity? Of course, it's plus, so it's concave up there. All right, so let's go. We just figured out that when we're looking for concave up, right? So we want to know 1/2 and higher. So if I come over here, here's a half, 1/2 and higher. So where is the overlap? Where were we decreasing but concave up? I'm trying to get my highlighter here. It's right in this region, right in that region. From 1/2 to 2 is when this thing is concave up and decreasing. Because over here we figured out from 1/2 to infinity, it's concave up. So the overlap is in this region right here that I've highlighted. And that is 1/2 to 2. Is that one of the answers? It sure is D, and that's the correct answers. All right, we got one more video to finish out the multiple choice without the calculator. All right, good luck.